most are dying. Only a few clones are living, and you can make a cell line from this primary culture. The cultured cell senescence can be provoked by various stresses, including the enforced expression of cancer-promoting genes. This oncogene induced senescence is linked by several known cancer pathways such as p53 and p16 and also RB pathway. It was thought initially that senescence could be an artifact caused by unusual culture conditions. For example, calf serum you added in your culture medium has a great effect for these artifacts, because usually you use 10% fetal calf serum. In case you use 15%, cells are all died, the most cells in culture. And these artifacts are dependent on the high concentration of fetal calf serum. A lot of other factors are known, but the fetal calf serum is the best known. You see an overview of only few parameters damaged DNA by X-ray or drugs or whatever leads to apoptosis. Involved is p53, BCL2, the Bugs family, p21, and also the RB. And this leads to another pathway which are not in the nucleus. Also, the cytoplasm is also involved by chemical or radiation. It's the most, from the mitochondria, the most factors, such as the BCL family and also the caspases. The caspase cascade, it started by a defect of the mitochondria. And this leads to apoptosis and the DNA damage. This is only a very small picture which factors are involved now in the G1 phase to the S phase. And you see the RB phosphorylated and leads to defects and also defects on the DNA. Here again, p53 phosphorylated leads to apoptosis and DNA damage. And ploidy changes, it's advanced in cancers, often have an increased DNA content per nucleus. That means more than 5.8 picogram. Unbalanced DNA synthesis and incorrect separation of chromosomes to daughter cells during the mitosis are two contributing factors. But amplification of specific DNA segments also occurs. The net result is a DNA content per cells that is not a simple multiply of 2. Diploid or 4 means tetraploid. and this is known as an aneuploid DNA content kills their host faster than do diploid tumors. It's also well known in breast cancer. An amplify of growth factors receptors like those that determine growth factors and amplification of the multi-drug resistance genes have recorded in many tumors. And cell death is a normal process that serves two functions: tissue remodeling and removal of damaged cells that might otherwise harm the rest of the body. DNA is constantly being damaged, and also the repair mechanisms exist but are not wholly effective. To prevent unwanted consequences, cells have a method to detect such defects and committing suicides. In embryogenesis, extensive remodeling occurs in which some cells are removed or other expanded. And this is a normal effect. Especially as embryo, you have between the fingers, it's a skin. And this skin will rebuild by apoptosis. It's a normal effect. Integration of proliferation and death is essential for normal homeostasis, and the processes are linked tightly such that death occurs even in rapidly proliferating cells. It follows that the equilibrium between proliferation and death is altered. Then a normal growth occurs. In carcinogenesis, unregulated proliferation or decreased cells that will generate a tumor. And what is apoptosis? It's a programmed cell death or cell suicide. Apoptosis requires mRNA and protein synthesis. So apoptosis is a normal process involving in situations required tissue remodeling, and extreme sample is the embryogenesis, that's like the skin between the fingers. And cells must have the ability to coordinate proliferation and apoptosis in response to external stimuli. This occurs in both normal cells and cancer cells. But in many cancer cells, the gene changes lead to decreased apoptotic death, and it leads to increasing in cell number. Apoptosis is also important in determining response to treatment like chemotherapy or radiation. So, for example, in a tumor, after X-ray, you find a lot of dead cells, apoptotic cells, as an effect from the X-ray. Under the microscope, the most striking features are the pattern of chromatin condensation and the appearance of membrane-bound apoptotic vesicles representing cell remnants that are removed by phagocytosis. And the features of apoptotic and necrotic cell death is the morphology in the apoptosis. Affected cells are single, the cell volume decreases, the chromatin is more dense, lysosomes are intact, mitochondria are normal, and no inflammatory response. and the sulfate are apoptotic bodies. In the necrosis, for example, leads by hypoxia, changes in pH or temperature. In necrosis, you find affected cells as groups, the cell volume increased, DNA or chromatin fragmented, lysosomes abnormal, mitochondria abnormal, inflammatory response is visible, and it leads to the lysis of your cell. You see here, this graph is 100 years old. Therefore, I show this. It's handmade. I have this table. I found this table in a very, very old book. You see a viable cell, and on the upper stage you find the apoptosis, cell shrinks, chromatin danced, and the budding, this body, and apoptotic bodies which can be removed by phagocytosis. In the case of the necrosis, the cells become sleepy, makes blooding, and cellular and nuclear lysis cause inflammation. And this is the same. You see here the necrosis and the apoptosis with the apoptotic bodies. And these apoptotic bodies you can also measure by flow cytometry, because the DNA content of these apoptotic bodies decrease more and more. You see cell culture, it's normal, and after incubation with drug, you see this effect. It shrinks more and more. Apoptotic bodies build up. Here in a light microscope by hematoxylene eosine, you see here the apoptotic bodies, and this is by fluorescence. The red cells are intact cells, and only the green cells are apoptotic. And the measurement by flow cytometry looks as this. You see here a normal cell, G1 phase, the S phase, and the G2 phase. In front, it's clear. After giving a drug, you see the G1 phase, a very, very low S phase, and a very, very low G2 phase. That means you have here a separate peak in front of the G1 phase, and this is a sign for apoptosis. Apoptosis which are coming from the G1 phase, the S phase, and also from the G2 phase. And this degradation of the DNA you see in front as in sub-G1 peak. And the microscopic, you see here the apoptotic cells. It's coming from here, and here you see normal intact cells. The cancer biology is a very, very complex science, as you have seen. And daily new factors and parameters, such as proteins, genes, are found every day in another factor. And to compare all these parameters is a work for Sisyphus. He was in Greece a philosopher. I thank you for your attention. questions.
I have just one question. So, the checkpoint for cell cycle can be considered as a marker for tumor treatment or prognostic factor like p53?
The marker for the checkpoints
Yes.
are P53, I quote.
Yes.
In this marker, we can localize the increase of P53 level and see if there is an effect for whatever. Also, the RB is also in the cell cycle nearly the same places like P53. And you use antibodies against P53 or P60 or P21, you can solve this problem, whereas the checkpoint is interrupted.
Rob?
Yeah.
You said when we increase the serum level, if it's 50%, that leads to cell death.
Yeah.
Why?
In this concentration, the FPS is toxic. In this concentration, only a few cell lines, tumor cell lines, need about 12%.
20,
12.
12.
12. But normally you work with 5% to 10%.
If we use 20 or 30%, that's toxic for the cells?
It's toxic for the cells.
Normal cell.
Yeah.
Primary cell culture also?
Cell culture?
Primary cell culture till third to the fifth passage is not.
No.
Oh yeah. Because I used
But
that, but it was good.
After this,
Yeah.
it's
Yeah.
really toxic. Yeah.
Just for 2 weeks only, then we shift to 10%.
Yeah.
Yeah.
You have to release the concentration.
Yeah. Because sometimes cell lines need in the beginning we start with a high concentration
Yeah.
of serum because it's very weak. It needs serum more maybe.
Mm-hmm.
Then after that it's become healthy and we can reduce it.
Yeah. And you see it. The cells are
Yeah.
shrink.
Yeah.
You can see it. And so you reduce the concentration of FPS. You see, cells are growing well.
Well, it was the opposite. When I increased the concentration in the beginning, the cells is growing better. But after 2 weeks, then I shift to the 10%. It becomes normal.
Yeah.
So I start with high concentration, then I end with the normal concentration.
It's a normal condition, and cell makes a differentiation
Yeah.
and proliferation.
Yeah, because you know when you got it from -80 or from liquid nitrogen, we preserve it for a long time,
Yeah.
and it was in a bad preservation like this.
Yeah.
Yeah, when you started. So I think the cells need a little bit to become healthy in a short time with the high concentration of serum, sometimes like that.
Yeah, and you use DMSO for freezing
Yeah,
or glycerin?
DMSO.
DMSO.
Yeah.
DMSO is also toxic.
Yeah, we wash it directly after I got it. I wash it.
After throwing, you wash with
Yeah.
normal media.
Yeah.
Yeah.
I wash it
Yeah.
before I use it in the high concentration of serum.
Yeah.
I start with that for 1-2 weeks, then I shift to the normal one. I use this method. I see it is it's better than I start with 10% because it's not healthy when I got it.
Mhm.
after preservation. It's not healthy.
Yeah. But in case the next passage,
No, I use the regular concentration.
regular,
Yeah. Yeah. Okay.
and have in mind the DMSO makes also exogenic effects. That means your DMSO makes heat,
Yeah. Yeah.
and therefore, in case you freeze your culture, you prepare all in ice to remove this exogenic effect.
Mm. Mm.
It's really necessary to prepare all in ice
Mm.
to remove these effects.
When I start to preserve it and I put the DMSO,
Yeah.
it should be in the ice.
Yeah.
Okay.
And after thawing,
Mm.
at the first step until the wine is thawed, you have to work very, very quickly because this exogenic effect is also coming.
Yeah, but we thaw it within 3 minutes in a 37 water bath.
In water, but
Yeah. So
But not-
directly then we wash it.
and immediately washing.
Yeah.
Yeah.
Okay. Thank you.
It goes. It's not.
I think you are so tired you need to rest.
Sorry?
You are so tired you need to rest now, huh?
No. I will look with Huda.
Yeah, oh my God. God bless you. مسكين ما حيرتاح.
لا لا لا. Just we will show you the proliferation format here, and then we will pick it up to water to complete your rest. Okay. And I have to introduce Mrs. Halla. She was the one who presented the first lecture.
Nice to meet you.
Halla, she's
Doctor.
the
It's my pleasure.
For me also.